Yes, okay. Okay, thank you. Hello, everyone. Good morning and welcome one more day to a CAP seminar. Today we have with us someone from this house, to Jacobo Aguirre. Many of you already know him, but if you don't, I would like to point out that Jacobo is a physicist. He has a permanent position here at the Center for Astrobiology since 2021. And his research focuses on theoretical and computational modeling of the evolution of complex physical and biological processes. Currently, he applies complexity theory and complex network science to astrobiology, particularly to the study of viral evolution and the origin and early evolution of life. And just for you to know, Jacobo founded the astronomical group of the University Rey Juan Carlos, and the technological company Complexity Killed the Cat. I love that name. And today he's going to talk about the emergence of interstellar molecular complexity explained by interacting networks. So if you are ready, we are ready.
Thank you very much. Thank you all of you for being here on site and online. And thank you organizers for giving me the opportunity to explain you here my work. This is what I'm going to talk to you about today. And this work has been done in collaboration with 3 other people. Miguel García Sánchez, he was with me here 1.5 years ago doing a master's thesis. He's right now doing his PhD in Comillas, la Universidad de Comillas. Fernando Puente, most of you must know him. He developed his PhD here with Víctor Parro, and right now he's in Uppsala in Sweden. And Izaskun Jiménez Serra, she's also here, as you know, and she's an astrochemist that has helped us to connect all the work that we've been doing here in more, if you want, a technical point of view and very abstract to astrochemistry and to real cases. Okay, first, let me start very briefly presenting the people who are working with me here in my group. And then I will focus on the work that I want to detail today. Okay, we are these people here. We are organizing a group called, well, we have to find yet a permanent name, but it could be like a complexity and astrobiology group. And we are part of this group of prebiotic chemistry and physics of complex systems here at CAP. Marina Fernandez-Ruth, she spent a year with us, and now she's about to come back to start a PhD. Co-directed with Marta Ruiz and me. Sofia Backlund, she just left, but she's been here for a year. And Adrián Aguirre Tamaral, he is a postdoc, and he'll be with us for the next months with funding of the Maria Maestro. All right, what do we do in our group? The main objective is to develop research connections to build a bridge, if you want, from astrobiology to complexity theory, understanding by complexity theory, which is quite it's not very clear for many people, complex network theory, game theory, mathematical and numerical modeling of complex evolutionary systems, etc., etc. And which is the specific objective? Our specific objective right now is to study the emergence and growth of complexity in the different steps from the origins of life till today. All right, let me present very briefly a couple of richer lines that we have before I get into details. I have created this table in order to present to you how complex networks can be interesting in different steps in this long way from the origin of life till today, and how we are interested in several steps, and we're having like several works in parallel in different moments of this long way. Okay. I'm going to talk today about the emergence of a complexity in the interstellar medium. Here, the nodes of the networks could be atoms, for example, and the networks could be simple molecules that you can find in these molecular clouds. Marina, she's been working till now, studying theoretically complex astrochemical networks, in particular, the chemistry of the interstellar phosphorus. In this case, each node is a simple molecule, and a network is a chemical network. Okay, so it's a step in this way till to life. Next, we have Adrian working on and developing a computational model to study the first RNA replication or protein replication. And in this case, the nodes are, if you want, simple molecules, and the network could be monomers or polymers. So we are in a step ahead. You know? And now, finally, Sophia has been working in the interaction between protein networks in the sense that how we are studying in different moments of an infection, how a virus attacks a human cell, and we're trying to understand how the protein network of the virus interacts with the protein network of the host. So as you can see, we are studying different steps, but in all cases, our tools, our formal way of working is more or less the same. All right, so let's focus on this. Emergence of interstellar molecular complexity explained by interacting networks. This work, in fact, well, let me first do a basic introduction to the concept of digital organisms, in case you don't know what they are. The astrobiology strategy of NASA 2015-2025 asks, what can we learn about the evolution of early life from artificial life? And in fact, so it's an open, important question in astrobiology. In the last 20, 30 years, artificial life based on digital organisms has been intensively developed. What are they? In general, they are computational models where mutations, evolution, competition, reproduction are fixed usually by external rules. In fact, all this, you say that it can be, actually all these works have a seminal basis, which is the Conway's Game of Life. By the way, Conway, he was a genius and he died last year of COVID, unfortunately. He presented this very, very simple system in which a pixel could be dead or alive, and it could reproduce depending on 2 or 3 very basic rules, just depending on whether their neighbors were dead or alive. In this very simple, the simplest way of understanding life that you can imagine, surprisingly, thousands of different patterns appeared, and no kidding, more than 1,000 papers have been written just based on understanding this simple. So this is the simplest way of life that you can imagine. However, 20 years later, different, much more complex systems start to appear. This is what we really call digital organisms. For example, in the case of Corwar, is the same, and Tierra, what we have is different codes, program codes that fight against each other just in order to try to control the resources of the computer. So the programs start to copy and they try to fight. And in that sense, it's like different organisms trying to fight and evolve. In Corwar, they're able actually to mutate in the sense that sometimes the lines of the code can change. This could be, usually it's very bad, but sometimes this can be positive, just as it happens with real evolution. In Tierra, it's quite nice because in Tierra, what they try is to get the code closer, shorter and shorter. And in this way, if you make it shorter and it works, then its fitness or its speed of reproduction grows. And so you can see just as how a real genome could try to lose genes and start to evolve faster and faster. So in this sense, you can see that they are trying to really model real life. Anyway, right now, the one that is usually used, and you can still find it in very, very important papers, is Avida, which is much more complex than the rest. And actually in Avida, you can even select those codes that are able to answer several questions. For example, whether if a code is able to say, if you say 2 + 2 and they answer 4, then its fitness grows. And so in this way, you make that the different codes can learn themselves and evolve. So there's a huge amount of work in here. Where is our work? Our work is in the middle of the extreme simplicity of the game of life and these core and Tierra much more complex systems. You will see that we're going to do a model that is as simple as possible. And then we'll try to find whether this can give us some information about real systems, in particular in astrochemistry. All right, let's start with NetWorld, which is this computational framework that we have created. And what we're going to do is to model the evolution of simple networked structures. We're going to create like a universe of networks that interact and evolve. By the way, in our case, complex networks represent actually anything because it's completely arbitrary. But you can imagine that they are representing simplified chemical compounds and they're interacting very, very simple rules. Okay, we're going to show that a drastic transition towards complexity appear, which is quite important. But all this, as I told you, this will be the next 15 minutes. All this will be based on network science theory and game theory. So there is no astrochemistry, no biology anywhere. Okay. However, the curious thing is that our results explain quite well the emergence of molecular complexity in interstellar clouds, where we suppose that the most basic bricks of life are created. And so at the end of the talk, I will talk about this bridge to real data and how they surprisingly fit quite well. All right. I'm not going to give you all the details of how network works. If anyone please ask, and I will explain it later. But in a few ideas. The first one, we're going to start first always with isolated nodes. So we're not starting with already complex structures because we want to understand how complexity appears from nothing, from the most basic stuff. You have 20, 40, 60 nodes. Each node is whatever you want, an atom, for example. These end nodes interact to form more complex structures, following some rules. And these structures, in every step, they can be divided. They can break with this probability. This probability, it depends on mu, which is the stability of the network, in the sense that if a network is very well connected, then it's more difficult to break it than if you have like two big structures and there is only one link in the middle. So it's a basic idea of understanding that things that are very well connected are more difficult to break than the ones that are very weak. But the important point, and this is critical for the talk, so pay attention now. Beta is the parameter, the only external parameter of the model. Beta represents the environment parameter. That is, beta represents the environment. Different temperature, different radiation, different amount of interstellar dust, whatever you're studying in ecology, in astrochemistry, all the context, all the environment is given by a value of beta. So it's a very simple system, okay? If beta is very, very large, then the probability of breaking is very small, and so you let things grow. But if beta is very small, the probability of breaking is very large, and so you have like a harsh environment, and so everything that you create gets destroyed. So this is more or less the basic idea. All right. Now, let's see an example. Imagine that you start with 4 different nodes. Imagine that, for example, these 2 can get together. From there, you could get to a network of 3 in a row. You could go back because you could lose one of them. You could go to this place and stop there. So you can do all this system is stochastic, and the computer will decide which are the ways that happen in each time. In particular, okay, the main question is, okay, Jacobo, you haven't told me how these networks interact. Give me some details. This has nothing to do, the rules of the interaction have, the main idea is that they have nothing to do with chemistry or physics or biology, okay? Actually, I took them from a former work in which I was studying the interaction between social structures and trying to understand how very simple structures like in the Paleolithic or on small tribes try to interact to grow and make much more complex and heterogeneous societies. So in a sense, I actually did it in purpose to make sure that the rules of the game are very basic and have nothing to do with what we want to model. Imagine that you have 2 networks, very simple ones, 3 in a row and 2 in a row. Actually, they are the most basic networks that you can have. When they get together, it's like a chemical reaction in some sense. You choose one node in A randomly and one node in B. For example, 2 and 5, this one and this one. And you put a link there. If 2 and 5, if both nodes win in a quantity that we call dynamical importance, if they win in something, then they keep this link. If they don't win, they don't want it and they reject it, okay? Second rule, each node can only have one connection with the other network. So if you have already one connection, you have to decide whether you want the new one or you want the old one. What is this quantity that they want to optimize? This dynamical importance. Dynamical importance is very related to a concept called eigenvector centrality, which is a way of measuring the importance of a node in a network. It measures how important your neighbors are. You calculate it studying the spectral properties of the network. It's very easy. It's based on the eigenvalues and eigenvectors of each network that we all studied at the end of the school. So it's a very, very easy algebra, but it's very important. And if you don't trust me, trust Google, because this is the model, the system that Google uses in its famous algorithm PageRank to order in importance the web pages that you can find. For example, if you write, I don't know, Shakespeare in Google, you will have like 10 or 15 different web pages. The first one will be the one that has the largest PageRank. In this case, the largest dynamical importance, the second one, the third one. So, and we have used the same or very, very similar quantity to understand whether a node is important or not. So I know that I skipped the details, the mathematical details, but I guess you get the idea. Two links between two networks are accepted if and only if each node wins something, wins in importance. Of course, this gives rise to a very complex system of, for a while, of throwing links from one to the other. Okay, they keep on interacting, and then finally, where does this finish? It can finish in two situations. The first one is that the two networks in contact, they finish in a what we call in game theory a Nash equilibrium, which is a system in which you don't evolve anymore because all the nodes would lose something if they changed. Okay, so they're more or less happy. Sometimes, however, we found out, this was surprising, that you don't reach to a unique structure, but you reach a circle, a cycle. From C, you go to this one, and from this one, you go to this one, and perhaps it's 4, A to B, B to C, C to D, and D to A. In that case, we choose one of them randomly. This is more or less like RNA, that you know that RNA can fold in different structures. This is more or less the same, that you have to choose one of them. Okay? So, what do we have here? I will explain it very fast again. You start, in this case, with 20 or 40 different nodes, and you let them interact, and they go growing. So in that sense, we have created like a chemistry of networks. And there are simple rules to make that when two networks get together, whether they interact or not. And what do you have at the end? An example. Imagine that we start with 20 different nodes, number of networks. After 20 steps, you have like 3 in a row, several pairs, and many of them independent, isolated nodes. Here you have some complexity. You can have like 2 or 3 different networks that are destroyed. After some time, you start again with very basic stuff. And finally, after 550 steps, more or less, you get to this complex stuff, and then you reach a final big node of 20 nodes, big network of 20 nodes, and you stop there. Okay, this is something I'm going to talk all the time from the point of view of ecology, and I guess that can be easy for you. We have here an ecology, in some sense, an ecology of networks. It's a very crazy idea, which is the diversity. The diversity is made of all the structures that you have found sooner or later. This is our organisms in our environment, which would be in this case beta equal 2.5. Okay, in this environment we have all these different structures. What is the abundance? Just the number of times that each structure has appeared in our process. If one structure is all the time appearing, it will be very abundant. Otherwise, it will be not. And if you have never seen it, then of course you are not in this diversity. Okay, more or less clear. Okay. Let's describe the ecology that our network creates. Let's look at this first. The size of, let's go here. the first thing to do is to measure how many different structures, how many different networks our system creates depending on the environment. I remind you of something. Beta is the environment. Small beta means that you have a very harsh environment in which everything you create, you destroy it. So look at this. Number of configurations. For low betas, we have like 1, 2, 3, 5, 10 different structures. You have like a square, 3 in a row, very simple stuff, okay? However, this is critical for this talk. There is a point in 1.55 where this exponential growth changes completely. And look at this. Even in 1.5, we have like, I don't know, 30, but in 2.5, we have 5,000. So in some sense, what are we having here? For small betas in very harsh environments, what you have is that the environment is so strong that you can create difficultly, but you can create the most LEGO, if you want, structures, LEGO bases. But in some point where you let it grow, this basic stuff, these basic structures are finally able to interact. And suddenly you get a huge explosion of diversity, because now you have 10, 20 basic stuff, basic structures, and sufficient abundance of all of them to start to play. Okay, so here you are surviving like in a desert if you want, and here you have the jungle. All right, look at this. The size of the structures. We're starting with 40, so the 40 is the biggest structure you can have. If beta is small, you only have structures of size 2. Each node, each blue node here, each blue plot or blue dot is just one network. So look at this. We have here the maximum is, I don't know, 3, 4, 5, 6. The sizes are very small, but whenever you cross the limit, you get 20, 30, 40 very, very big structures. And how is there entropy? Entropy means the complexity of the structures. Some of them will be, some of them here are very simple and have a, look at this, this is more or less the same. It's like a square put several times. So the complexity is very small, but you also have this kind of very complex stuff. So take home message, if the environment is very harsh, then you only have very small structures that can try to survive as they can, but there's a critical point in which if you cross it, all these motifs, basic motifs, can start to interact, and then you have a huge amount of diversity. All right, I had forgotten the idea of abundance. What does abundance have to do here? And in ecology, that's important. If we measure which are the most abundant structures, as you can imagine, the most abundant always is the isolated node, because it's what you start with. But then if the probability of breaking starts to get smaller and smaller, here appears the 2 in a row, 3 in a row, 4 in a row, a small basic star, and then after 1.5, after the critical, then you have hundreds and thousands of different structures. Look at this. Believe me that here there is a nice transition, and you can measure it also this way. If you measure the normalized entropy, Shannon entropy, which is very typical in ecology, it's a way of measuring the complexity. Look at this. It is clear, it's showing clearly a transition. Something happens in 1.5, okay? From a different point of view, let's use another tool typical of ecology, the abundance ranks. The abundance rank curve is very easy to understand. If you have different species, you just put in order of the most abundant to the least abundant, and you put the abundance of each of them. So this line here would be the most abundant one, the second, the third, the fourth, okay, for different environments. If the environment is very small, sorry, if the environment is very harsh, low beta, these curves are more or less exponential. This is the critical one. But if you grow beta, this is important because the curve that used to be exponential becomes power law, becomes of this size, of this way, if you want. And this is important because it's the typical thing that you expect when you see a rare biosphere, a rare chemosphere of individuals that introduces diversity in the system. So this is typical of ecology. In very harsh environments, you have exponential distributions, but if diversity explodes, then you have a long tail of lots and lots of different structures that are not very abundant, actually are very rare, but there are lots of them, okay? Waiting in ecology for their opportunity to grow, for example, in the sea. So this is more or less what I wanted to tell you in this part. We're playing with isolated nodes that they start to interact and they create things. If the environment is very hard, you only have very basic stuff, but suddenly if the environment is not so hard, you let things grow and you have nice biodiversity there. So in this point, we arrived to CAB like 2 years ago, and we started to think, where can we apply this? Which is the system, the most basic system where we could apply it. And we contacted Izaskun Jimenez Serra, and she told us, we have to look in astrochemical stuff, because in these molecular clouds is where the most basic molecules are created. All right. And so this is what we did. The molecular clouds in the interstellar medium show a quite complex, actually, structure with different physical regimes. Up to more than 250 different molecules have been detected, so there are a lot. When the amount of dust grows, because the molecular cloud is collapsing, the external interstellar UV radiation starts to be attenuated. And this is important because in the first steps, the ultraviolet is so strong that it destroys almost all the basic molecules that are created. However, when we get to this critical point in which the dust is, the extinction is enough, is sufficient to stop this or attenuate this ultraviolet radiation, all the molecules that were there already start to interact and they start to give dozens of different molecules. So we thought, hey, this resembles surprisingly what we've been doing. Let's compare our predictions that, I remind you of this, have nothing to do with real data. We don't use real data. We don't use deep learning. We don't use fitting of real data. So our results are completely artificial. Let's compare our results with reality, with this real system. What do we have here? Surprisingly, well, we have taken 4 different molecular clouds. Ufiuchi-Chi, which is a diffuse molecular cloud where the extinction is so low that there are no more than, this is this black line, no more than 10 different structures, okay? A second one is a translucent cloud where the extinction is just in the limits between a diffuse molecular cloud and a dense cloud, and 2 dense clouds where the diffusion or where the extinction is so large that molecules can grow easily. And look at this. Oh, by the way, this is, I didn't tell you, this is the abundance rank. So this is the number of different molecules, and this is the abundance of each of them. The first one is hydrogen, CO, etc., etc., etc. Okay. Ufiuchi has like 10 different ones. This Sagittarius B2K4 has like 20. There are 40 in L134N, which is in serpents, and TMC1, which is in Taurus, has around 60. All right. If we use our system for different betas, we obtain these curves, which are quite similar to what we have here. And in fact, the critical line, the one that is just the critical point in which magic starts to happen, it is this brown line, if you want, also coincides with this Sagittarius, which was what we expected to see. In fact, not only qualitatively, but also quantitatively, the results are quite good. If we compare here, the TMC1, Taurus TMC1, and Serpents L134N, and their abundance with what we expected, the dots are real stuff, and the crosses are our predictions, we can see that they're quite good, okay? Of course, they are not the same, but I remind you of the fact that we're using a completely different system. So it's quite surprising that they, both qualitatively and quantitatively, they seem to meet if we normalize them correctly. All right, then. Not only that, and this, I think this is a very nice thing of models. Sometimes the models, as this one, are too difficult, are too simple to explain you really what things happen. But they can give you some hints, some tips of new points of view that perhaps you see something, and this something might not be the same in reality, but it makes you look for several patterns or several behaviors in reality that other people had not thought of. And this is what happened here. We were very, in our system, in NetWorld, in this computational framework, we were very surprised that the abundance of the curves, or the abundance of the different structures that we appeared, didn't correlate with anything. And finally, we found that they only correlate with one thing. This is the abundance of different structures, but I'm talking about the networks, a square, whatever. They correlate very well with the number of paths that can be found to create them. That is, imagine that 5 different paths, starting with 4 different nodes, 5 different paths give rise to a square. What this is saying is that the square will be more abundant than if these 4 have only one path to create a line, for example. So the more ways a structure, a network is created, the more abundant it is. Does this happen in reality? Does this happen in the universe? Does it happen in the biosphere? In the biosphere? Is it true that in the universe, the more different ways that you have to create something, a molecule, I don't know, an organism, whatever, the more abundant it will be? It seems reasonable, but it definitely is a very complex question. So I decided to look at this data that we have in astrochemical databases, and it asked me in this case, how can we measure the different chemical paths that give rise to CO, to H2, to methane, etc. And she said, this is quite complex, but she gave me a fantastic answer, and it is that CIDA is a great database, which it's free, it's in the internet, where you write the molecule and it gives you the number of reactions that have in any astrophysical environment this molecule as a product. You put, I don't know, H2O, and it would say, it's an example, 250 or whatever. This means that there are 255, it's an example, I just invented it, different reactions that can give rise to H2O, to water. Okay, so we crossed this data, number of reactions, against the abundance, the real abundance of the molecules in TMC1 and in this other molecular cloud. And again, surprisingly, we find this kind of relation that is exactly the same that we found in our model. It's of this type. It's a very simple. The abundance goes as the number of reactions or the number of paths up to alpha, where alpha is a bit over 1. We're not saying that there is a causal relation between both things. What we're saying is that sometimes reality has basic patterns that have to be followed, and there are not so many. There's not so many ways to create life or to create complexity. And well, physicists are very used to finding universal classes, but other people don't. So we are not so surprised for this kind of thing. But still, in this case, I think this is a totally new result, and we just found it because we looked from the correct point of view. That's something nobody had done yet that before. All right, so conclusions. We have introduced a computational framework called NetWorld, in which very simple nodes start to interact, and they create networks, and these networks interact and divide. And this gives us if you want, a chemistry of networks. I remind you of this point, no connection with chemical rules at all. There is a transition towards complexity in a certain point, beyond which we have like this big amount of diversity. Our predictions, surprisingly, quite reliably mimic the molecular evolution in the interstellar medium during this transition towards what they call complexity. And I would like to remark the point that they point out some unknown astrochemical relationships that had not been seen. And of course, we have to be able to explain them now. This is the problem, but they are there. At least we have something to work with. Okay, take-home message. our work, in some sense, supports that some properties, many properties that rule this long way from astrochemistry, from the chemistry in space to biochemistry, and from the beginning of biochemistry, and from there, or prebiotic chemistry if you want, and from there to life as we understand it right now, show quite simple and general patterns. And these patterns can be studied formally and can give us a lot of information, even from real processes. And well, we have to be careful in some sense, because as they used to say, Doctor Who in this famous BBC series, I love humans, always seeing patterns in things that aren't there. But it's true that physicists love looking for patterns, and I do, and they sometimes are useful. So this is what I wanted to tell you. Thanks a lot. And any questions will be, I will try to answer it as well as possible. Thanks.
Thank you very much. Wow. Can you listen to me? Okay.
Thank you, Jacobo. It's just a very naive question because, you know, I understood your talk from a very basic. I was wondering if you say when you explain, when you try all these interactions between the nodes, and they are apart from any chemical, biological, or whatever context, how does it work to test how they interact? It's just probabilistic numbers, mathematics, without any, how? How kids explanation, I mean.
What we do is the following. We start with n, for example, 40. So most of the things that I have shown here are for 40 initial nodes. There, you choose two of them randomly, which will be 2 nodes, and they get together. Okay, and then from there, you can find 2 different nodes or a pair and 1 node, and they start to interact. This interaction is based on what I explained it, but it's true that I just explained it very basically, not to give details, but I can give a bit more now. Imagine that you have already a network of 5 nodes and a network of 10 nodes. It's like 2 molecules, and they get together. So we just do, we put randomly 1 new link, 1 new connection from A to B. If this is accepted because the 2 nodes really win something, because they really become more important topologically connected to other people, then they accept that. It's actually, it comes from socio-economical models, where you can understand it better. Imagine that you have I don't know, 2 tribes, and they get together, and one person in one tribe knows one person in the other tribe. This friendship will only be accepted socially if they both win something with this connection, and then they keep it. Then 2 other people also get connected, and they will also, only if this new relation that you have, this new friendship is good for you, then you maintain it. And this is what we do in life. Let me finish. And sometimes we don't let them have 2 friends for simplicity, in the sense that time is I mean, we can't have 1,000 friends. So whenever you have 1 more, you have to erase one of them. And so what they are trying to do, what the networks are trying to do, is to become more efficient and more better structured. So it's not physics. It's a question of network science, of trying, each node tries to be in a better situation. Talking about, imagine information that is moving around or things like that. So it's based on how, so the nodes try to connect just if they think that in the new network, they're going to be better connected.
But then what you consider to win in this context is just quantitatively speaking, it's higher
it's a quantity that is based on, actually it is the maximum, technically, when you have a network, you can convert that network in a matrix. In a matrix where a link is a 1 and no link is a 0. It's called the Disentangling matrix.
Okay.
In this matrix, you can calculate the maximum eigenvalue, which it's a very easy quantity that gives you how strong the network is, how big, and also the maximum eigenvector, which gives you, this is what I told you that Google does, is very similar. It's a quantity that has to do with how important your friends are. If your friends are important, then you're important. And we multiply those two quantities. So in that sense, this is the mathematics we do. In that sense, it's a way of measuring the importance of a node, but it is completely mathematical. So it's a quantity, it's 0.05. If this is bigger than what you had before, you keep it, otherwise you don't.
Okay, thank you.
Bye.
Thanks, Jacobo. Very interesting talk. So it seems like the key here, we already explained almost this reward concept, which is the largest eigenvalue matrix. But so it seems like the key here, because your net world model seems simple, unless there's more technical details that you didn't tell us. But it seems like the key here, apart from this reward concept, is the mathematical form of your probability. So you didn't explain where you got that. Was this just a wild idea, or is there a reason to pick your mathematical form for P?
Okay.
So could you explain the index I on it? What does that I mean?
I just means the number of the node. Node I1, node 2, node 3, so it's an index. Here, what we wanted is a probability that decreases with beta. That is, we want a probability where for some betas is very large, and if beta grows, this decreases. The easiest way perhaps could be, we have like two possibilities, an exponential of minus mu beta, okay? Or this kind of curve, which is quite similar. And this is like, if you want, it's very similar to one of those sigmoidals, but we put a 2 in the sense that when beta equals 0, we want that the probability is 1. So we want that if beta equals 0, everything that you create, you destroy it. It's true that I remember that you told us that this was related to, it's true, to other kind of, if you want
Fermi-Dirac.
for the Boltzmann, no?
Fermi-Dirac.
Fermi-Dirac is, yeah. And I looked that up afterwards, and it's true that it is the same structure. It's very, very similar. But this is the more or less the idea, to find the easiest function that decreases exponentially with beta. But we could have chosen, actually we did the same with other kind of probabilities, and the results are.
Okay, that's an important point, I think. So in other words, you're saying that the model is robust to mathematical changes in your form of the probability. Is that what you're saying?
At least whether if you have like an exponential decreasement, actually the difference between this curve and an exponential decreasement is very, very small.
Okay.
Actually, in the limit they're the same.
The next question I have, because I find it very surprising that you only need to have one parameter beta. Okay, now imagine a situation where the environment can only be described with 2 or 3 or 4 or 5 parameters. Then what would you do? Will you have to generalize your net world model? I just find it surprising that you only need one parameter. That's what surprises me.
Actually, in all systems, there is more than one parameter, for sure. Also in this case, in the case of the astrochemical molecular clouds, you don't only have this extinction. You have temperature, you have many others. This is the simplest system you can find. Probably, if we had, I have no idea, but what I would guess is that you have several parameters and all of them are equally important. Probably this model would be insufficient. I guess we should have to put a new one there or do it in a different way. It is true that we have looked in the real system that we thought could fit the best. It is true anyway that we also found that in ecology, also this was done by Fernando Puente, who is an expert in this subject. Also in ecology, we have found systems that are very, very similar. For example, we found a very nice PNAS work on the deforestation of a jungle, where they could see that these curves that I said of these abundance rank curves of the abundance of the different organisms used to be these very, very long tails. And after deforestation, they became completely exponential, and they found a drastic transition in this case towards the destruction of nature, which seemed to fit quite well also with our curves. So it seems that it is quite general, as far as, of course, the system is sufficiently simple. You cannot do miracles. And if the system is so simple, if the model is so simple, you need simple systems. But it seems quite general.
And since you're also getting, in some regime, power laws, this reminds me of self-organized criticality. Does this have anything to do with self-organized criticality and the models of Pierre Bach and the Copenhagen school?
I haven't looked at that. Perhaps I should, but I haven't done it. It is true that power law distributions appear everywhere. So it's hard to say whether this is a system of SOC or not. I don't really know, but it's a good idea.
Okay, thanks.
Another question here. Okay, we have a couple of people on Zoom chat that want to tell you something. Victor Rivilla, you can open your microphone if you want.
Okay, can you hear me?
Yes, we can.
Okay, thank you, Jacobo. Very, very nice talk. I think that these applications are really interesting, in particular, those in astrochemistry, which is my field. I have a comment on the relation you have found, both from observations and from your code, between the number of paths or the number of reactions and the abundance of the molecule. I find it that this is quite intuitive in the case of the model, because the most routes you have to form a system, you would expect to have it more abundant. In the case of the observations, I think that it can be partially affected by historical reasons, because the most abundant molecules were detected, which are the brightest, so they are the easiest to detect. So they were detected decades ago. So for this reason, the people in the lab and developing chemical models have worked on trying to understand how these molecules are formed in the interstellar medium. And then you have in the KITA database a lot of possible routes to form them, just because the people have worked on these things for decades. On the other side, if you has just discovered a new molecule, it's usual that there is no single formation route in the databases, just because the molecule was not detected. So anyone, nobody was trying to understand how it is formed, because there was no detection. So in that case, you will have a lower abundant, because it's a molecule that has been recently detected, just because it's quite low abundant, and then it's more difficult to detect. And you will have a zero in the number of reactions in the database, because nobody till now has worked on that. So I think that this historical reason can be at least partially affect this plot you show on the left panel.
I am sure you are completely right. In fact, one of the referees wrote, no kidding, 2 whole pages telling us all the biases that we should put into the paper and analyze, and we did it, and it is completely true.
I was not the referee.
You were not?
No, I wasn't.
Bad luck. I would have loved that. Here, he's asking about these abundances, that they are full of biases. There is a huge bias on the size of the model, of the molecule. Because in the beginning, of course, they only could detect, astrochemists could only detect the smallest ones, 3, 4, 5 nodes, 3, 4, 5 atoms. And not only that, there are many molecules that cannot be detected because they do not vibrate in the correct way or whatever. Well, there are several of them. In fact, what we did there is to make sure, well, here's also asking about, it is true, that even in KITA, in this database, whether they say that there are 100 different reactions to give rise to water, doesn't mean that they are all equally probable, for sure. Probably in most cases, there are only 2 or 3 or even 1 reaction that is the important one. And the rest could be there, but as Victor said, you don't really know. It is true that's why we're so surprised in this result. What we did anyway, in order to make sure that this correlation exists, is we could do something. In this case, we do not only have the abundance in the databases and the number of reactions, we have one more detail, the size of the molecule. These are real molecules. Some of them are have 2, 3, 4, 5 atoms. And so we studied very deeply from a statistical point of view, this correlation, and we could see, we did the partial correlation study, which means that we studied this abundance with relationship with the number of reactions, making sure that the dependence on the partial correlation on the size of the molecules did not affect. You can do that. You have two correlations, a correlation between two quantities, and you want to make sure that these two quantities correlate without taking into account a third quantity. This is called partial correlation. You can do it, and we did it, and it works. So at least the bias on the size of the molecules does not affect this result. And this is quite important, because the size of the molecule is the main source of biases. It's true that there are other ones that should be studied in detail, but it is also true that here, don't forget, Victor, that this is logarithmic and this is also logarithmic, which means that all these dots that are underneath are very far away from the line. In some cases, they can be like 1 or even 1.5 orders of magnitude over and underneath. So it is true that we're putting there a lot of noise, a lot of errors, but the relationship is there. But I agree with him completely. I mean, actually, it's true that one of the referees was very, I wouldn't say only surprised. He or she was even worried. I would say, I mean, this cannot explain everything, and I agree completely. This cannot explain everything. But still, surprisingly, even when we've been able to erase some biases, the correlation is there.
Thank you.
Okay, we have another question from Juan Ramal. If you want to open your microphone, or if not, I can read it, your question. But if you want to talk? No? Okay, I can read it. So
no, sorry, I'm here.
Okay, all yours.
Can you hear me? Yeah?
Yes, sure.
Okay, thanks, Jacobo, for the talk. It was quite interesting. So, but I have a doubt related to the initial notes. As far as I know, the relationship is purely statistics, right? How do you discriminate the real interactions, which are based on the law of quantum mechanics, from those which are purely speculation? Everybody knows that one atom of hydrogen and another atom of hydrogen cannot be, let's say, joined in the gas phase. So normally it's in solid phase. Is one example, as many others. Oh, how do you separate the real interactions from the, let's say, speculations or not proactive reactions in the molecular clouds? Thanks.
I don't understand very well your question. You mean, how do I discriminate in my model? Or
yeah.
In my model, there is no real data at all. So our model has nothing to do with quantum mechanics, nothing to do. In my model, we have only networks that have very simple rules to get connected. And these rules, as I said before, are based on network science. I don't know, perhaps I didn't understand your question.
Yeah, what I mean is the relationship between molecules in order to form third entities are normally ruled by the quantum mechanics. No. If you introduce a huge number of interactions, many of them will be, let's say, probably speculation because they are not going to be formed. What I thought is, if you introduce any correction in order to obtain the real number of interactions that can be produced in the molecular clouds, for instance.
Okay. I think I understand now. You're not talking about my model. You're talking about when we get the information from CINTA and from
and as well according to the results, because you finally are going to be compared those results with the real interaction that are being produced in the molecular cloud, right?
Okay, actually, we don't even do that. We just, this is why it was so astonishing for us. We just go into CINTA and we get the number of reactions that are there. I know that many of them, most of them, will never happen or probably will be very difficult to happen. But still, imagine that it would be a huge and terrible work to go one by one, seeing which are the main reactions and choose them. We just get the whole number. That is why this correlation is has to be, of course, analyzed in detail. Because I agree with you that most of the reactions will probably not happen, but we couldn't choose. And actually, whenever you choose, you're starting to put biases into the data. So we just get the information from the database, the abundance that we find in the papers, and we use that. And it seems to work. But we do not anyway change any detail. We just get a completely arbitrary model, we get results, and we compare them with what we get from the databases. And that's all. We don't do any kind of fit or we don't study, we don't choose the molecules, the reactions, we don't put biases, we don't do anything at all.
Okay, thanks.
Okay, any other question? No? So thank you very much, Jacobo, very interesting talk. And for the rest of you, see you next week for the next seminar. Thank you.
Thank you all, bye-bye.